Hello everybody. I'm Teemu Laajala from University of Turku, Finland, and I'll be presenting our L0 pseudonorm regularized regression modeling framework that we applied in the DREAM anti-PD1 challenge. And here is our DREAM team. On the top row from University of Turku, we have Anni and myself. We were in charge of the mathematical modeling side of things. And on the bottom row from University of Helsinki / Helsinki University Hospital, Tuomas Mirtti and Mikko Mäyränpää as our clinical experts who provided very valuable information during the challenge. So the premise for us going into this challenge that we were already developing an L0 pseudonorm modeling framework when we spotted the challenge itself. So we thought, okay, this looks like a good chance to test and benchmark and improve our modeling framework. And lucky for us, we had already implemented Cox regression for survival outcomes, which was essential for sub-challenges 1 and 2 for progression and survival, respectively, as well as a logistic family for binarized outcomes, which would be sub-challenge 3 for best overall response. And we teamed up heavily with our clinical experts throughout the challenge, as we heard from the previous speakers as well. They provided us guidance on immuno-oncology, for example, giving us hints on genes that might help distinguish between hot and cold tumors, which we already heard about, as well as giving us very valuable information on the predictive aspect of the challenge, which I highlight is extremely difficult. So we had to always be non-informative towards chemotherapy predictions while maintaining informative predictions towards anti-PD1. So this was something also where they contributed. So they contributed across the whole challenge from transcriptome to tumor mutational burden, as well as the associated clinical variables. And we found out that this is really essential, especially given that there were large gaps in the data that we were able to obtain. So what is L0 pseudonorm? It's essentially the number of non-zero regression coefficients in a regression model. It's also known as best subset selection. You don't typically hear about it that much because it's a little bit of an under-researched field inside regression modeling, mainly perhaps because it's a very complex optimization task. It's very discrete and non-continuous by nature. Lucky for us, we have an ongoing collaboration with the optimization group at Department of Mathematics and Statistics at the University of Turku. I have to name out Kaisa Joki and Marko Mäkelä, who have helped us formulate L0 pseudonorm regularization as a difference of two convex functions and provided us with an algorithm for solving for that target function. So apologies for the pixelated images, but on the left-hand side, you can see L1 penalization, also known as Lasso, which was part of the formula shown by the previous presenter. And as a function on the x-axis, you can see that as we increase lambda, which is the penalization coefficient, when we go towards the left in the figure, the number of coefficients that deviate from zero shrinks. So we effectively eliminate them out of the regression model. On the right-hand side, you can see OSCAR, which is our name for our methodology in L0 pseudonorm regularization. It's a slightly different approach. On the x-axis, instead of having penalization, continuous penalization, you have cardinality, which is essentially the number of non-zero coefficients. At each discrete point, you see a non-zero coefficient pop out from the zero axis. And as is very custom for this type of modeling tasks, we selected the optimal complexity via cross-validation. So if you're interested in hearing more about the optimal subset cardinality regression, which we dubbed our method, OSCAR, it's openly available in GitHub. We have put out a CRAN package with an implementation, as well as we have a preprint out where we showcase this methodology in prostate cancer. Regarding this particular challenge, I'm echoing largely my previous talkers here. The data was really king here. We were able to obtain 2 good chemo arms and a supporting chemo arm from TCGA, LUAD, and LUSC cohorts with very good annotations, very good N counts and such. But where we stumbled upon some roadblocks was really obtaining those anti-PD-1 data sets. Might be too small to see, but the key message here was that we were only able to obtain one data set that contained NSCLC samples, and even there in Pratt et al., it was only a subset of the samples therein. So mainly we're extrapolating transcriptomics results from melanoma, essentially. But in addition to that, while we might have gotten nice transcriptome coverage, we would have also wanted the additional supporting variables such as tumor mutational burden, PD-1 stainings, tobacco use, gender, which were not always available, which is a shame. So that was also posing to us a modeling challenge. Here you can see, sadly it's a little bit cropped from the top, I guess. You can see one of the advantages that we did leverage is that we observed from the data as well as from the literature that the three endpoints corresponding to the three sub-challenges were heavily correlated. So you can see on the top hand annotations with white and black. On the top row, you can see the third sub-challenge, which was the binarized responder versus non-responder. And then the two next annotations are progression and survival capped at 1 year time point. They are follow-up based endpoints, so obviously you have censoring there. And as you can see from this heat map annotation, they go very nicely hand in hand, and this is from Guide et al. Melanoma data set. We observed that throughout the data. And leveraging this information that we were able to kind of utilize these endpoints, we were able to identify a reliable 5-gene panel. And those 5 genes were CD274, CXCR6, CXCL9, TIGIT, and PDCD1. And maybe for others, it's obvious that CD274 would be informative because it's the coding gene for PD-1 ligand. Additionally, we would hypothesize that CDXCR6 and CXCL9, which partially overlap with some of the genes that we saw from previous presenters, might be indicators for a chemokine storm. We also identified additional candidates which were also overlapping with the previous presenters, like CD8A, but I'm not going to talk about them more because they were not part of our ultimate submission to this particular challenge, but would be interesting for future. So obviously we had challenges inside the challenge. So like I mentioned, we stepped into the challenge while we're developing a modeling framework. We're essentially working on a method. So it was really a race against time. We were fixing bugs in Fortran, including Fortran 77, which is not something that you'd really want to be doing during a DREAM challenge, and adding new essential features to our OSCAR R package. And from the modeling perspective, on the other hand, the scarcity of suitable data, we've heard about it enough today, it was really a big challenge. Finding those data sets, we really couldn't find NSCLC to the degree that we would have wanted to. And even when we found some promising data sets, they were incomplete in regards to TMB and other clinical variables. Also, the T-cell, B-cell repertoire information, which would have been very interesting to model, but we couldn't do it because we couldn't obtain data. Something to point out also, which I would like to see more in DREAM challenges, is all our work is public in GitHub. So you can see me and Anni struggling throughout the challenge in trying to figure out where there is signal and where there's not. Here's an example performance ROC AUC curve, where on the left-hand side, you see our data sets in sub-challenge 3, where the best overall response binary outcome is what we're trying to predict. On the left-hand side, you see example data sets where we were not able to obtain nice ROC AUC of ranging from 0.7 to 0.8 across the data set. Here, the predictions are based only on the 5 genes that I outlined before, and they were combined together into a score via GSVA, gene set variation analysis. But something to keep in mind regarding this challenge was that it was a predictive modeling challenge. So on the right-hand side, you see especially the TCGA, Lusk cohort, and Brown et al. therapy arms. So always when we were trying to figure out an informative model, we had to pay attention to the left-hand side to get informative signals, but on the other hand, we had to be random on the right-hand side, which would be the x equals y axis, the random ROC AUC of 0.5. And the final model that we were able to obtain is really a linear model combination of terms. And I need to stress out that the first term, which had the heaviest weight, is really the result of this regularized regression. On the other hand, the rest of the terms were more or less based on literature, as well as a clinical expert who provided us with crucial information, as well as our gut feeling as modelers and really a lot of the modeling going on between the years. So putting together, first term was a result of modeling, and the others are a kind of a symbiosis of a priori information and small snippets of data across the field. And also since the endpoints were correlated, we submitted the same model to all three sub-challenges. And I believe, since it's not yet public, I can't talk too much about the results, but I believe we were doing quite well, especially in sub-challenges 2 and 3, and that's why I'm here today. So thanks for your time, and here's some acknowledgements and funders, and thanks obviously to the DREAM organizers and community, and I'd be happy to take questions.
Hi, excellent talk. Just wanted to ask one question, which is basically related to the L0 norm. So the L0 norm is known to be non-convex, and as a result of which, when you try to use it, you might, with different multiple initializations, you might get different set of features. So how do you basically counter that to come up to a fixed set of panel?
That's a good question. So I believe I need to repeat the question. Oh, I don't. So the L0 pseudonorm is extremely difficult to optimize. I want to have our optimization group right next to me to consult. Basically, it's a lot of heuristics. There was a paper coming out just in 2019 or 2020 in optimization field, where they showed how to do this as a differentiation of two convex functions. And Kaisa, for example, has specialized in those optimization tasks. So a lot of heuristics are involved, and I acknowledge it's very sensitive to, for example, starting points and such. So we're utilizing multiple starting points and trying to do a lot of heuristics to support that. Right now, we're still working on improving that. And yeah, it is a difficult optimization task. And that's probably why you don't see L0 pseudonorm that widely in use. There's very few of them out there.